Hello. This video includes information on bond energy.
This is actually the last thing we need to go over. It's called bond energies. So it's a little bit different than the enthalpy of reaction values we were just talking about. It's still energy though. It's dealing with the energy that's required to break bonds or released when making bonds. So when we talk about bond energy, it's related to the strength of the bond, okay? And bonds are what hold atoms together in a compound. So the stronger the bond, the more energy is required to break that bond. Okay, and it's important to know that when we break chemical bonds, energy is required. It's an endothermic process. You have to add energy in order to break chemical bonds. But when we make chemical bonds, energy is released, or it's exothermic. And the energy required to break a bond is specific for that covalent bond in 1 mole of a molecule, and it's called our bond energy, or you might see it called the bond dissociation energy. So if we had X bonded to Y, we would have to add in energy to break this bond. Now remember that this line represents the sharing of a pair of electrons between X and Y. So when we break this bond, one of the electrons stays with X and one of the electrons stays with Y. And we would kind of signify this with a D. This is for our bond dissociation energy. So the bond dissociation energy for X bonded to Y is equal to the delta H for that value. It's the energy that's required to break that bond. Now, it's going to tie in Lewis dot structures because you have to know what's bonded to what and whether there are single bonds, double bonds, or triple bonds, because the bond strength is related to whether it's a single bond, double bond, or triple bond. So let's say we look at a molecule that has multiple bonds. So this is methane, CH4. It's got carbon bonded to 4 hydrogens. Each of these bonds needs to be broken. And this bond requires 415 kilojoules of energy. And this bond requires 452 kilojoules, or 415 kilojoules of energy here, 450 kilojoules of energy here. So the total amount of energy to break this molecule up into carbon and hydrogen would be 415 times 4, or 1660 kilojoules of energy. This is a bond energy table. Okay, after we look at a problem, I will put it back up there on the screen. You do have access to it in the PowerPoint that you can see, but let's just kind of just look at it for a second. It's got 3 columns. So we've got here, and then we've got here, and then we've got here. It tells us the type of bond that we're looking at, and it tells us the bond energy in kilojoules per mole. So if we wanted to break 1 mole of hydrogen-hydrogen bond, we would need to add in 436 kilojoules of energy. Now, the reverse would be true as well. If we wanted to make 1 mole of hydrogen, we would release 436 kilojoules of energy. But it's always going to be written in terms of breaking the bonds. So they're always going to be positive values, endothermic. If we wanted to break 1 mole of hydrogen carbon, we would need to add in 415 kilojoules of energy. Now look down here. Here's a carbon-carbon single bond. Okay, for a mole of carbon-carbon single bonds that we want to break, 345 kilojoules of energy need to be added in. But if we had a mole of double bonded carbon, we would have to add in a lot more energy. And if we had a mole of triple bonded, we would have to add in even more energy. And that should make sense based on what we've done in the past, because triple bonds are stronger than double bonds. And double bonds are stronger than single bonds. So since single bonds are the weakest, they require the least amount of energy. And since triple bonds are the strongest, they require the strongest or the most energy. Or we've got nitrogen single, double, triple bonds. Notice that the bond energy increases as we go along. And that should make sense. In no way would you have to memorize this table. It would be something that you would be given, or in the context of the question, the information would be there. And you just have to know what to do with that information. Oops, those numbers shouldn't have gone in there yet. So pretend those numbers aren't there yet. So let's say that we want to deal with the enthalpy change for a reaction. It's going to approximately equal the sum of the energy required to break all the bonds plus the energy that's released to make all the new bonds. So if we start out with reactants, we would have to break all the bonds on the reactant side first, and that would require energy. And then the atoms would rearrange themselves and form new bonds on our product side, and that will give off energy. So our equation, when we talk about bond energies, we can calculate the enthalpy of reaction by taking the sum of, that's what that sigma sign is again, the sum of the bonds broken minus the sum of the bonds formed. And the reason we're going to do it this way is because the table tells us the values for breaking the bonds. If we want to make the bonds, we're essentially just flipping the sign on the information that's in the table. And that's what this negative, this subtraction in the equation does. It essentially flips the sign on the table. Okay, so now you know where those 415s came from. So let's say that we have CH4, and we're going to react it with O2, and we're going to produce CO2 and H2O. So you can kind of see from this that you have to remember how to do Lewis structures so that you know what kinds of bonds are involved. This particular question gives it to you. So we're going to have to break 4 carbon hydrogen bonds. So we're going to take 4 times 415 kilojoules. We're going to have to break 2 oxygen-oxygen double bonds. And each of those bonds being broken requires 495 kilojoules of energy. So all of this here has to be added in to break all the bonds on the reactant side. That's what the sum of the bond energies being broken comes from, this part here. So now the atoms are going to rearrange themselves. We're going to form carbon dioxide. And in order to do that, we would have to make 2 carbon oxygen double bonds, one here and one here. And we would have to make 1, 2, 3, 4 oxygen hydrogen bonds. And each of those would release 463 kilojoules of energy. And that's where the sum of the bond energies on the product side comes from. So 4 times 415, that breaks all of these bonds. Plus 2 times 495, that breaks all of these bonds. Then we're going to subtract from that 2 times our carbon oxygen double bonds plus 4, 1, 2, 3, 4, 4 times our oxygen hydrogen bonds. And we find out that this reaction overall has an enthalpy of reaction value of negative 800 kilojoules. So let's look at another one, and I'm actually going to have you practice your Lewis dot structures as well. It says use the bond energies to calculate the approximate enthalpy change for this reaction. So we've got carbon monoxide reacting with hydrogen to produce CH3OH, which is methanol, but we don't necessarily need to name that. So the first thing I want you to do is write the Lewis structure for carbon monoxide and for each of our hydrogens and for our CH3OH. And I'll give you a minute to kind of remember how to do that. We're not going to do any math yet. You're just going to write your Lewis structures for our reactants and our products. Okay, so for carbon monoxide, you have 4 plus 6, so you have 10 electrons to work with in your Lewis structure. For hydrogen, you have 1 times 2, so you have 2 electrons. And then for our CH3OH, you've got 4 plus 3 plus 1, or sorry, plus 6 plus 1. So that gives us 4, 5, 6, 7, 8, 14 electrons. Okay, and I get some Lewis structures that look like this. If we don't have the right Lewis structures, we're going to look up the wrong values on a bond energy table. So carbon monoxide has a triple bond. Each of our hydrogens has a single bond, and that makes sense. Hydrogen can't do anything but make a single bond. And then CH3OH is going to have 3 CH bonds that are going to be formed, 1 CO bond that's going to be formed, and 1 OH bond that's going to be formed. Because once you have this down, I'm going to go back to that bond energy table and see if you can find out the enthalpy of reaction using the bond energy table. So there's our bond energy table. You've got a carbon oxygen triple bond, which is here. You've got hydrogen hydrogen, which is here. You've got carbon hydrogen, which is here. And you have hydrogen oxygen, which is here. So add up all the energy that has to be added in to break the bonds, and then subtract the energy that's released when you form your bonds. Okay, so we need to add in 1,080 kilojoules of energy to break this bond. We need to add in 436 kilojoules of energy to break this bond, but we have 2 moles of it, so we're going to have to multiply that number by 2. This is the total energy that has to be added in to break these bonds. Now we're going to look on the product side. We've got 3 carbon hydrogen bonds, so 3 times 415. We've got 1 carbon oxygen bond, so 350. And we have 1 oxygen hydrogen bond at 486. So we add this together, and that's the amount of energy that's being lost or given off when we form our products. So the sum of the reactants minus the sum of the products gives us our reaction.